So obviously, we jumped to a different screen. I've rearranged things, but I didn't want to bore you with erasing things and rewriting and whatnot. So what I've done so that you can see the calculator more clearly is I've listed all of our zeros that we found from P of X on the left, and here I have my calculator. And I also needed to play around with the zoom so that I could show you some things, and I wasn't really sure where to go, so I spent a couple minutes zooming around. Not really something that you want to watch. But here are our zeros, and so you can see that we have 1, 2, 3, 4 real zeros. And as we mentioned previously, complex zeros come in pairs. So 4 real zeros and 2 complex zeros. And we're going to see that on the graph of P of X. So here in my Y-editor screen, I have typed out P of X, x minus 4 squared, x plus 7, no exponent. The next factor is x squared minus 9, and I just simply put all of these in parentheses. I type it out the same way it's written in the workbook, and our last factor is x squared plus 2x plus 3. This factor is where our complex zeros come from. And now if I hit graph, and I go to my standard view, you can see that the graph of P of X just simply looks like a series of straight lines. But you should also see that we cross the x-axis. Okay, we don't see the maximums or minimums, but we cross the x-axis 3 times that we know of. And then here, since we're so zoomed out away from the graph, okay, the graph of P of X is sort of, it has really large upper and lower limits in terms of y, and then it's sort of scrunched in within a small area on the x-axis. But these 3 zeros are x equal negative 7, x equal negative 3, plus 3, and then this piece up here actually drops down and touches the x-axis, although the graphing calculator doesn't really do a good job of drawing that piece. This is our positive 4, 0. And so we only have 4 x-intercepts. And they're shown here. So what I'm going to do is just simply zoom in here on the x equals plus 4. I'm going to basically draw a zoom box in this area to show you that x equals 4 simply comes down to the x-axis, touches it, and then shoots back up, which makes sense according to the properties of polynomials that we just talked about. This exponent indicates multiplicity of 2, which is even. So that's the sort of behavior that we expect, just to simply touch the x-axis, not to actually cross it. So here we go. I'm going to zoom in. And I'm going to erase these marks I made over my graph. I want to hit zoom box. Here's my cursor, and I'm going to draw a box around x equals 3 and x equals 4. And so you can actually see the turning point. It comes down from left to right, and then it just barely touches the x-axis, and then it shoots back up towards the right. Okay. And so if we looked on our table at x equals 4, we could sort of get a second witness to the graph and see that we have at x equals 4, 0 and 3, y equals 0. And so at 5 it goes back up on the y-axis. Okay, so that pretty much completes what we can say about p of x. And we will carry on to the next page. C, we're sort of working backwards. It wants us to construct the polynomial least degree with x equals 0, negative 2, 1, and 5 as the real zeros, with the factor or the 0, 5 having multiplicity of 2, and 1, x equal 1, 0 having multiplicity of 3, and we want to construct one with degree 6. Okay. We will call it little f of x, and so we'll simply go through here and fill out the factors according to the zeros that we have. So x equals 0, then x must be one of our factors. If negative 2 is one of our zeros, then x plus 2 must be a factor of our polynomial. We have x minus 1, so we simply write x and subtract the 0. So here are the 4 zeros, or the factors as a result of the zeros that we were given. Then it tells us that the 0, 5 being originating from this x minus 5 factor has a multiplicity of 2, so we simply assign this factor an exponent of 2, and then 1, which would be this x minus 1 factor of little f, has a multiplicity of 3, so we assign an exponent of 3 to that one. So what is the degree of little f as it is now? We have x squared, x to the third, which makes for 5, and then we have 2 x's here, which would give us a degree of 7. Moving on to example 7, it reads, for the following polynomials, factorization cannot be easily obtained. Use graphing techniques to estimate real zeros. Also determine the number of complex zeros. So we're simply going to use our calculator, and we are going to type in p of x into the y editor. So p of x has an x to the third, a plus 3 halves, and to play it safe I put 3 halves in parentheses, followed by x squared. Then I have a minus 18x along with a minus 25, enter, graph. I sort of redraw my graph using Zoom Standard, and if you look here and notice that the degree of p of x is 3, then we have at most 3 zeros. Okay, and looking at the graph, we see 3 x-intercepts. 1, 2, 3. So if we reread our question, it wanted us to estimate those zeros. We go to second calculate. Number 2 on the calculate menu is 0. And we'll start from the left, most 0. If we go to the left of this first 0, we drop down below the 0, so I hit enter. Now I want to go to the right and hit enter, and then enter again. The calculator gives us x equals negative 4.3, and if I round it to the nearest hundredths, I get 0.33. Now I want to calculate my second 0, so I hit second calculate 2. Arrow over close to the second 0. We're still in the negative half of the x-axis. I'm to the left of the second 0, so I hit enter. Now I hit the right arrow key. Cursor, you can see the cursor drops below the 0. It's now on the other side. We hit enter. Enter for a third time. And we will round this. We get some crazy decimal number. X equals 1.38. Now for our last 0. Same procedure. Arrow to the left, and it drops below the 0 that I want, and I am looking at this x-intercept. So I'm to the left, I hit enter, move my cursor to the right, it jumps up past the x-intercept, enter again, and then enter a third time, and it reads x equals 4.20 if I round it. X equals 4.20. So graphically, it's super simple to find the zeros of a polynomial, barring the case of where the polynomial is spread out across the x-axis, and so you have to zoom around quite a bit. Most of the polynomials that we are going to plot, you can usually locate the zeros by simply going to the Zoom Standard view. Alright, so p of x had at most 3 because the degree of p was 3, and we had 3 real zeros, negative 4.33, negative 1.38, and 4.20. For f, we have a new function or polynomial. Into my y editor, I type minus x to the fourth plus 6 plus 6 x to the third power arrow over to the right, minus 3x plus 3, enter. We graph it. We're already in the zoom standard mode, and now we see only two x intercepts. So what is the degree of p of x? Degree is 4. So that means that we have at most 4 zeros. So here are two real zeros, and if you'll notice, you see this feature of the polynomial where it looks like it breaks towards the x-axis, it hits a local minimum, and then it shoots back up, and later it returns back to the x-axis, crossing it at our last zero and continuing downward to infinity. So we have at most 4 zeros, and we only see 2 real zeros. Therefore, you can conclude that we have 2 real and 2 complex. Once again, this feature here with the curve downward towards the x-axis but not actually crossing, dropping all the way down to the x-axis, this is usually indicative of complex zeros. So what we'll do is, as before, we will calculate the 2 real zeros. Graphically, we are out of luck when it comes to calculating the complex zeros. So for the first one on the left, I get x equals negative 0.94. So x equals negative 0.94. That's our first real zero. And now we'll repeat the same procedure. Second, calculate number 2, 0. And I'll arrow over to the right till I get close to my last 0. So if I hit the right key, I see my cursor there, and when I hit the left key it jumps off the screen, so I'm gonna sort of roll the dice here and just assume that it is to the left of this last 0, and I'm gonna hit enter, and now I'm gonna arrow over to the right and hit enter again and enter for a third time, and it lands right on top of the x-axis, and I can read x equals 5.93. For my second real zero, and then all we know is that there are 2 complex zeros left in this polynomial. So that completes example 7. We will scroll on down the page to see what's next. We run into a definition. Definition 5 states that a turning point of a polynomial is a point where the polynomial changes from increasing to decreasing or vice versa. So we're really looking at maximum and minimum, local that is. Next we have properties of graphs of polynomials. It reads p of x be a polynomial, degree n, leading coefficient a n. The graph of p of x has the following properties. It is continuous and smooth. There's no breaks in it. There's no sharp points. It's one solid piece. It has at most n zeros, which could all be real, all complex, some real, some complex, and so on and so forth. The real zeros are x-intercepts. It has at most n minus 1 turning points. 4. What about the end behavior? Well, if the leading coefficient is positive and the degree is even, then the graph of the polynomial will be up and to the left and up and to the right. So an example of that would be an x squared function. If the leading term or the leading coefficient is positive and n is odd, the degree is odd. So with n, you need to think degree, and so we're talking about degree is odd, and here we're talking about degree is even. In this case, an example of that would be x cubed, and this is just one example. Here we use the example of x squared, a u-shaped function. And so x cubed, in a way, if you start at the center and you go left, then you go down. If you start at the center and go right, you go up. So it's down to the left, up to the right. However, these end behaviors change if we change the sign of the leading term. So in this case, you could think minus x squared. The leading coefficient is now negative, it's less than 0, and so we would get a parabola that opened up downward. Then if we use the same example, x cubed, except now we make the coefficient negative, and so simplest case, in my opinion, is minus x cubed. We would now have a curve that went up to the left and down to the right, something like that. Now this also applies to higher exponents. So if leading coefficient is positive and the degree is even, then it can do it can curve around, create some maximum and minimums in between. But on the far left and the far right, the curve will go up on both ends. So even x to the 4th, x to the 6th, these would behave the same way, up to the left and up to the right. So example 8 has us doing that sort of thing. It says use the table above to determine the end behavior. So here we have polynomial p. We have an is less than 0. It's negative. Then we have degree is even. So with even degree polynomials, the end behaviors are the same. Left and right go up, or left and right go down. Now whether they go up or down depends on the coefficient. In this case, the coefficient's negative, so it would be a lot like the parabola that opens up downward. Here we have capital F function. The leading coefficient is positive. It's a +4. So it's greater than 0, it's positive. Then we have a degree that is even, or I'm sorry, not even, but odd. So the end behaviors are going to be different. One's going to go up, the other one's going to go down. Odd degree polynomial. Now since it's positive, we go up to the right and down to the left. So up, right, and down, left. What about Q? Well, we have an is positive again, but now our degree is even. And so I don't know exactly what this is going to look like, but it's going to be or have the same behavior as an x squared function that opens up. So we don't exactly know what it does in between the two ends, but we know that both ends are eventually going to go up and continue to travel upward indefinitely. So we would say up, up. And finally, capital R polynomial, we have a negative. A(n) is less than 0, a negative coefficient. Negative 2 is our a(n). The coefficient of the term that has the highest exponent. Then our degree of our polynomial is 5, which is odd. Alright. Working backward, I want to go back and make it clear where the even, the odd, and the even came from. So for capital P, the degree was 2, so degree is even, the highest exponent, and there's the degree 2. Here was the degree, the highest exponent 3, so I said degree odd. And then for capital Q, this is our degree, the highest exponent, 6, and degree is even 6. And so our degree here is 5 for capital R of x, and it's odd. However, the coefficient's negative, and so you need to think negative x cubed, and so right would be down and left would be up. Example 9 reads, explain why the following graphs do not represent graphs of polynomials. The first one's real easy to pick out the problem. We have these sharp points, so not a polynomial. Here, this one is hard to tell. Okay. But what you need to pick out is the fact that on the left we have end behavior that appears that it's going to go down and continue that way. However, the end behavior on the right of this one is not clear. It looks like it's starting to converge with the x-axis. It's not actually breaking up or breaking downward. It's just simply starting to flatten out. And so that is not indicative of a polynomial. Alright. This one, I would say is not a polynomial simply because we do not see it span the x-axis here. Okay. We come in from the right, if we go from right to left, which we usually don't do, but we come in from the left and it shoots straight down, and it looks as if the y-axis is a vertical asymptote. And so this doesn't really look like an x squared, because an x squared goes down, or I should say a negative x squared. We would have a downward end behavior on the left, and then we'd have a downward one on the right, and this one just looks like it's not really making a beeline for positive or negative infinity. It looks almost as if it's sort of like a square root function that sort of continues to positive infinity on the x-axis and simply gets flatter and flatter and flatter. So that's why we would say that this is not a polynomial. So the top two on the right, they were smooth, and they didn't have sharp points. but they didn't have definitive end behavior. Okay, this one down here, bottom left, is not continuous. It has a vertical asymptote here. And that could sort of be another explanation as to why this top far right graph was not a polynomial. This on the bottom left is looks like a rational function, so we say not polynomial. So the middle bottom function is arguable. It looks a lot like a polynomial. However, you should recognize that this is sort of exhibiting an oscillatory behavior, in that it simply oscillates back and forth across the x-axis, and as far as we know, it does that indefinitely. It never really makes up its mind whether it's going to continue to y equal plus infinity or negative infinity. More than likely, this is some function of sine, which is a trig function, or you could say sine x. Usually with trig functions, we look at them in the context of angles. So this could be sine x or cosine x. So this is not a polynomial. Again, no definitive end behavior. And the last one, sort of the same reason as this top middle function. Here we are sort of just simply converging with the x-axis. It doesn't break towards positive or negative infinity for the range. So this one is not polynomial. Example 10 wants us to consider little f of x, and we want to find the following properties. The degree, pretty simple to pick out, the largest exponent, 4. The leading term, 1/2 x to the 4th. And so this is the leading term, and the coefficient of that term would be 1/2. C, the possible number of real zeros, well, that would be 4. The possible number of turning points is the degree subtract 1. So in this case, that would be 4 minus 1 equal 3. E wants us to sketch the graph on a graphing calculator and answer parts F, G, and H. So F is the exact number of real zeros, so we have to graph it and find the x-intercepts. And G, we estimate the real zeros. And H, we estimate the coordinates of the turning points and classify each as local minimum or maximum. And then at the bottom of the page, we have a coordinate plane that we want to actually graph the polynomial on. So here is my calculator. To graph little f of x, we go to the y editor. I usually type fractions in parentheses. So we have 1/2 times x to the 4th minus x to the 3rd minus another fraction, 11/2, with an x squared behind it, a plus 6x, and then a plus 10. Once it's entered into the y editor, hit the graph button. And looking at the graph, we see that we have 1, 2, 3, 4 x-intercepts, and the most zeros that we can have is 4. So we found all of our zeros. There are no complex zeros. We also have 2 local minimums and a local max, which we can't see on the graph yet. We'll have to zoom out for it. So I'm going to erase this and go to calculate to get the values of my x-intercepts. I'll start from the left and work my way to the right. The calculator asks for a left bound. Now I hit the right arrow key, it skips the x-intercept. I hit enter and enter a third time, and I get negative 2.70. And we're going to have 4 of these. So the second one, same procedure. Second, calculate 0. Enter on the left. Enter to the right, enter a third time, and we have x equals negative 1. Our third 0 from left to right looks like it's going to be positive. We are on the left. We arrow past the third 0 to the right, hit enter, enter a third time, and the calculator gives us x equals 2. And for our last 0, enter, move the cursor to the right, enter a second time, and then a third time, and we will round this 0 to 3.70. Now, F, okay, we've sketched the graph on the calculator, obviously. F, we gave the exact number of real zeros. There were 4, and there are 0 complex zeros. 0 complex zeros. There are none. Part H now wants us to find the turning points, the local minimums and the maximum. And I know I'm going to have to graph this eventually at the bottom of the screen. So I'll write down my x-intercepts one more time. Negative 2.70, negative 1, 2, and x equals 3.70. So with our zeros, we now want to go back to the same calculate menu, select minimum. We'll start with the leftmost minimum. Okay, move the cursor to the left of the first minimum, hit enter, move to the right, hit enter a second time, and then a third, and we want both coordinates. We want the x and the y, and I'll simply estimate that. I'll write down the local min. X is -2 and y is -8. The other one I'll write on the bottom right once I find it. Again, second calculate minimum. We arrow over to the right until our cursor is just left of the last minimum. Then we arrow to the right and hit enter a second time and a third time, and we get 3, -8. So it appears that both local minimums drop down to a y value of -8. Now we need to find our local max. So make sure that on the calculate menu you select maximum. I'm not sure if it's on the screen, but I'll try to calculate it without zooming around. We are to the left of the maximum. Arrow over to the right until you see the cursor drop down to the right of the maximum. Enter 2 more times, and the calculator tells us the coordinates are 0.5 and then 11.5. This is our local max. So now all we have to do is transfer our x intercepts, plot our local minimums and maximums, and do our best to trace a curve through those points. So here is -3, and I'm going to estimate 2.7 to be right about there for our first x-intercept. The next x-intercept is a -1, halfway between 0 and -2. We have x equals 2 exactly. And then our last x-intercept is almost 4. It's 3.7. So I'll plot a point just immediately to the left of x equals 4. Then we'll plot our local minimums. We have -2 and 8. So wherever those x and y coordinates intersect, and then we have -8 again for the second local minimum, and we drop down from x equals 3 in between 2 and 4. We'll plot that point. We will plot our local max at 0.5. So if here is x equal 1, 0.5 is right in between 0 and that mark. So we'll trace a vertical line up to 11.5. Y equal 11.5. Those two coordinates intersect, and we'll plot our maximum. So the end behavior, left and right end behavior of this polynomial, since the degree is 4 and the leading coefficient is positive, we are going to have up to the left and up to the right. So we'll sketch this the best we can. We will come down from the left, pass through the first x-intercept, drop down, touch and curve through the first local minimum, back up through the second x-intercept, curve up to the top of our local max, back down through the third x-intercept, and so our polynomial basically looks like a W. And then finally, once we pass through our last x-intercept, we simply travel upwards towards positive infinity on the y-axis, and so our end behaviors again would be up on both sides. So that's sort of an example of how the different properties of polynomials can help you sketch the graph of some of these functions. So on the next page we see two more questions regarding the previous example. They want us to find the intervals where the polynomial is increasing and decreasing, and then use end behavior to chart to determine the end behavior of the polynomial. Well, we sort of did that on the previous page. We said that an, the leading coefficient, is positive, and the degree was 4, and that is an even number. So the end behavior is up to the left and up to the right. Now back to I, we simply want to use the coordinates of our minimums and maximums. Remember that our polynomial simply looked like a W, and we only want to reference the x coordinates of the minimums and maximums. We had our maximum was located at x equal 0.5. Our first minimum was located at let's see, I'll have to bring up my calculator. And I'll just estimate it. I'm pretty sure it was around x equals -2. And then we had another one at x equals 3. And I'll double check that with my cursor. Yeah, 2.97 is pretty close to 3. So those may not be the exact coordinates. Well, actually they were. We used the calculate function on the calculator, so we can be certain of the x coordinates. And so looking at this W, we see that from, and we want to when working out the increasing and decreasing intervals, we always want to orient ourselves in the sense that we travel from the left side of the graph to the right side, from -infinity to positive. So for decreasing, which is the behavior or the interval that we first have on the left, it is decreasing from -infinity up until the first minimum, which is at -2, and we'll put parentheses on both limits. We could write union, and then our second interval where we decrease, and I'll highlight these in red. Here's the first one, -infinity to 2, and then the next one that is decreasing would be from 0.5 to 3. As for the increasing intervals, we simply have the other two segments of the W. Here is our first one in the green between -2 and 0.5, and then to the far right on out to positive infinity, from 3 to positive infinity. So our two intervals would be negative 2.5, both numbers with parentheses. Then we could plant a union symbol in between the two. The last interval is from 3 to infinity. So that only leaves us with one more example in this section. We have a box problem again. We saw this type of problem in chapter 1, and it reads, an open box is to be made from a square piece of material 24 inches by 24 inches. This is to be done by cutting equal squares from the corners and folding along the dashed lines. So if we cut these squares out of the corners, and then folded these sides up to make the sides of our box these long rectangular sides. There's 4 of them. If we folded those up, those would make the height of the box, and so our height would be x. In terms of the volume, we're simply following the formula length times width times height, and it doesn't really matter which you assign as length, width, or height. You simply want the 3 dimensions. So one of the dimensions is x. I refer to it as the height. And then the other 2 would be equal. The width, we could call it, is 24 minus 2x. If we cut the 2 squares off the corners, we now have a width instead of 24 minus the 2x pieces. And we started out with a square, and so if we cut 2x off of the length, then it would have the same expression as the width, 24 minus 2x. Now, here is our volume function as a function of x. B wants us to determine the domain and range of the function. So, in terms of the domain, which refers to i.e. x, we would say that our domain starts at 0. So if we don't cut any squares off of the corners, then we really don't have a box. So we could say that the volume of our box is 0. So that sort of sets the limit for the domain. As for the range, i.e. y coordinate, in this case, once we put this into our calculator, y is simply going to take the place of our volume. So we don't want our volume to be negative, so likewise the volume would start at 0. So our range would start at 0. And now, in order to get the upper limits of our range and domain, we need to use our graphing calculator. Or you may be able to figure that out algebraically, but using the calculator is usually pretty simple or easier. So once again, I will go to the Y editor, I'll type in my function for volume, just the same way that I've written it out with the factors. 24 minus 2x, and if you wanted to, you could simply square that, since there's two of them multiplied together. And when we go to our graph, we don't see anything, so we're going to have to play the zoom game. Now, one of the safest ways to do this is to use the window settings. And if you think about this function, we've already said that if x is 0, then we get 0 volume, so that's sort of a starting point for our x minimum in our window. But if you think about these other factors, 24 minus 2x, well, if we let x equal 12, if we inserted that into our volume function, multiplying 12 times 2 would give us 24, and then we'd have to turn around and subtract 24 from 24, and therefore our volume would once again be 0. So the upper limit of our x max should be around 12. I'll go a little past that and type 13 into my x max. And then I'm not really sure what the maximum volume is going to be. I will just pick a relatively big number, 100, and hit enter. And we will graph our polynomial again. So here we only see a small piece on the far right. Obviously we didn't pick a large enough y max. I'll go back and I'll pick 1,000. Probably way too big, but at least we know we'll see the top of the curve. And there's actually a piece cut off at the top, so we need to go a little bit further than 1,000. I will go to 1,100. Up, enter, graph, and there we see our maximum of our volume function. So where is the maximum located? For what volume do we have the maximum volume, and what dimension x gives us that volume? Real simple to figure out. The calculator does the work. We simply use the maximum function. We arrow to the left of the peak, enter. We arrow to the right of the peak, enter again, and enter a third time, and we get a maximum of x equal 4 and y equal 1,024. So we still haven't finished the domain and range. We've sort of already answered the limits of the domain, or the right limits. We said that we definitely want to cut out some square on the corners, so we can't say that x is 0. We don't want a 0 volume. So we really could go back and put a parentheses here instead of a bracket. Okay, if we don't want 0 volume, if we want some positive volume. And then if we use x equal 12, well, that's too much. We with x equal 12, we get a 0 volume box again. So I'll do the same for the range. I'll use parentheses instead. And for the range of our function, we use the maximum that we just found from the calculator, and that is 1,024. 24. So cutting squares from the corners, measuring x units between 0 and 12 will yield a volume that spans anywhere between 0 and 1024. With the coordinates of our maximum, you would have to realize that y is your volume. So Vmax would be 1024. So we actually have one more example, example 12. We're given a revenue function for a company from 2003 to 2010. T equals 3 corresponds to 2003. Okay. A says use a graphing calculator to approximate the relative extrema as well as intervals on which the revenue function is increasing and decreasing over its domain. So we'll call our calculator back in. We'll walk through R of x. Our first term is 0.168. 5. Our next term is plus 4.298, and instead of t we'll use x to the third, minus 39.044x squared plus 149.9t, and again x in the place of t, minus 185. Enter and graph. So this is the previous view that we had, and apparently our polynomial is a lot closer to the x-axis. I'll see if I can go into my window and simply decrease that to maybe y max 100. And it says that our limits for x or t are 3 and 10, so my x minimum and x max I'll simply put into the calculator as 3 and 10, and I'll see what the graph gives me. So between 2003 and 2010, our from the beginning, our revenue increases for a short period of time, then it hits sort of a local maximum. It starts to decrease and flatten out in between. Then in the later years it increases again, hits another higher local maximum, and then decreases to the end of our time frame 2010. So we start out increasing, then it decreases for a period of time. We probably hit a local minimum there. Then we enter into a long phase of increase in our revenue, and then on the final segment we are decreasing. So in order to nail down these intervals, we need to find these two local max and this local minimum. So once again, using the calculate function of our calculator, I'll scroll over to the left and find this first maximum, enter. Then I'll find, okay, I go to the left and then a right bound, enter a second time and then a third. And we'll write down both coordinates. We have x equals 4.1 and y equals 21.9 if I round it. This is our first local max. Then in between we're going to hit a local minimum. So same procedure, except I select minimum instead of maximum. I am to the left. Then I scroll to the right, enter a third time, and we get the coordinates 6, and our revenue is 18. And according to the problem, revenue is in millions, so that would be 18 million. And I'll round it to 18.8. And again, this is the local minimum. And finally, where is our local max to the far right? We move our cursor just to the left and then again to the right. Enter a third time. And so at x equal 9, or in other words 2009, we have revenue of 29.2 million. So now we're ready to write out our increasing and decreasing intervals. Increasing intervals, well, that starts at 3, and we probably want to stay consistent with WebAssign, so we'll simply use parentheses 3 to the first local max, 4.1. Then we pick it back up with the local minimum at x equals 6, and that function, the revenue increases to the last local max, 9. As for the decreasing intervals, past our first local max at 4.126, then we pick it back up again past our second local max from 9 to the last year, 2010. So our revenue function looks somewhat like an upside down W, with these local extreme being 4.1, 6, and 9, and the far left and right respectively are 3 and 10. So part B of example 12 reads, use the results of part A to describe the company's revenue over this period. Well, initially revenue increases until 2004, we could say between 2004 and 2006, the revenue decreases from, let's see, 21.9 million to 18.8 million. Then the revenue increases to, let's see, 29.2 million in 2009, finally from 2009 to 2010, or maybe you could say to the present, revenue decreases again. And so that wraps up section 2.2.